Hello, friends. Welcome to Science Talk. I'm your host, Jim Massa. Excuse me. I want to discuss with you some more tipping elements, thresholds, as the authors in this study put it. And this is a report published in the European Geosciences Union under the category of Earth System Dynamics. And interacting tipping elements increase the risk of climate domino effects under global warming. So we have Nico Wunderling, Jonathan Donges, Jürgen Kurtz, Ricarda Winkelmann are the principal authors. And they use the term tipping elements. I just posted a video that, the authors use tipping points. They also, in the body of the text here, discuss thresholds. And the more I think about it, I think threshold is probably the best way to put this. You reach a certain threshold, and then what happens on the other side of that threshold. So, go through the abstract here. With progressing global warming, there is an increased risk that one or several tipping elements, as opposed to tipping points, elements, in other words, the factors, in the climate system might cross a critical threshold, resulting in severe consequences for the global climate, ecosystems, human societies. While the underlying processes are fairly well understood, it is unclear how their interactions might impact the overall stability of the Earth's climate system. So, for example, we know what warming the air does to the permafrost in the Arctic, right? Thaws it out, methane is released, further warming. But how does that, say, perhaps impact crop yields? Or how does that impact sea ice loss? Are there interactions between the two? I'm probably choosing a bad example there, but to give you an idea of what's going on. But here's another one. We're losing the Arctic sea ice. We're having freshwater input into the Arctic Ocean. Does that freshwater stay in the Arctic Ocean, or does it get flushed out into the North Atlantic? Couple that with Greenland ice melt. Now, what do those two, the freshwater in the Arctic Ocean, the melting of the Greenland ice sheet in the North Atlantic, what are the interactions there? And then, of course, to the tie-in to Amok, etc. So these are some of the things that kind of the hints of what they're getting at here. As of yet, this cannot be fully analyzed with state-of-the-art Earth system models due to computational constraints, computing power, as well as some missing, uncertain process representation of certain tipping elements. Here we explicitly study the effects of known physical interactions among the Greenland and West Antarctic ice sheets, the Atlantic Meridional Overturning Circulation, Amok, and the Amazon rainforest using a conceptual network approach. We analyze the risk of domino effects, another way of saying positive feedback loops that exponentiate, being triggered by each of the individual tipping elements under global warming in equilibrium experiments. In these experiments, we propagate the uncertainties in critical temperature thresholds, interaction strength, and interaction structure via large ensembles of simulations in a Monte Carlo approach. The kind of a modeling methodology there. Overall, we find that the interactions tend to destabilize the network of tipping elements. In other words, the elements working on their own can cause problems, but there's a synergistic effect where they basically reinforce each other, and that reinforcement, because Earth is a complex system, everything's working together, it leads to a destabilization of all these networks of tipping elements that could basically push the planet into another regime, another system. Furthermore, our analysis reveals the qualitative role of each of the four tipping elements within the network, showing that the polar ice sheets on Greenland and West Antarctica are oftentimes the initiators of tipping cascades. Now, here's the interesting result here. While the Amoc acts as a mediator transmitting cascades. That's very interesting, but makes sense when you think about it. We'll discuss that later. This indicates that the ice sheets, which are already at risk of transgressing their temperature thresholds, the paras 1 to 1.5 to 2 degrees C, are of particular importance for the stability of the climate system as a whole. Well, that really should not come as any surprise, because due to the albedo, all that heat energy from is reflected off the ice sheets back into space. The ice sheets basically kind of act as a refrigerator for the planet and help keep the climate that has been for the last several hundred thousands of years, almost a million years. You lose the ice sheets and things can progress rapidly out of control. Okay. So, tipping elements in the climate system. The Earth system comprises a number of large-scale subsystems, the so-called tipping elements that can undergo large and possibly irreversible changes in response to environmental or anthropogenic perturbations once a certain critical threshold in forcing is exceeded. Once triggered, the actual tipping process might take several years up to a millennia, depending on the respective response times of the systems. A lot of variability, as you can see. Among the tipping elements are cryosphere components, such as the continental ice sheets on Greenland and Antarctica, biosphere components, such as the Amazon rainforest, boreal forests, coral reefs, large-scale atmospheric oceanic circulation patterns, such as the monsoon systems and Amoc. With continuing global warming, it becomes more likely that critical threshold of some tipping elements might be exceeded, possibly within this century, triggering severe consequences for ecosystem infrastructures, human societies. These critical thresholds can be quantified with respect to the global mean surface temperature, GMT, resulting in 3 clusters of tipping elements that are characterized by their critical temperature between 1 and 3, 3 and 5, above 5 degrees C of warming compared with pre-industrial temperatures, respectively. The most vulnerable cluster, which is already at risk between 1 and 3 C of warming, includes several cryosphere components, specifically mountain glaciers as well as the Greenland and West Antarctic ice sheets. In other words, the alpine glaciers. Recent studies suggest potential early warning indicators for these tipping elements, showing that some of them are approaching or might have already transgressed a critical threshold. Okay. Tipping elements in the Earth system are not isolated systems. They interact on a global scale. And this Lenton et al. Is being cited quite a bit. You can, for example, you can click on that. Maybe I'll just do that right now. Brings it right to the source here. Climate tipping point, too risky to bet against, appeared in Nature in 2019. Okay, so let's scoot back up here. These interactions could have stabilizing or destabilizing effects, increasing or decreasing the probability of emerging tipping cascades, and it remains an important problem to understand how the interactions between tipping elements affect the overall stability of our system. Despite recent progress in global Earth system modeling, current state-of-the-art Earth system models cannot yet comprehensively simulate the non-linear behavior and feedback between some of the tipping elements due to computational limitations. Okay, so let's pause here for a moment. What they're addressing there is the difficulty in trying to run the models for these interactions. The models are really good for example, saying, well, what happens, as the temperatures increase, what happens to the ice sheets, and as the CO2 levels increase, what the Earth temperatures do, that kind of stuff. So looking at individual elements, some of the models are actually quite good. But because Earth is an integrated system, trying to put the models together, the interactions, the synergistic, the reinforcements, if you will, that's where it becomes more challenging, and that's where the work needs to be done to improve those kind of modeling. That's what they're saying. They're not saying that all the models are bad. It's the models looking at the interactions that need improvement. So they basically looked at 5 tipping elements. So, of course, the Greenland ice sheet, the West Antarctic ice sheet, the Amoc, ENSO, Amazon rainforest. Those are the models that they looked at. And so then they present this diagram here. And I'll read you the figure here, and then I have an enlarged version so that we can look at it better. Interactions between climate tipping elements and their roles in tipping cascades. Greenland ice sheet, West Antarctic ice sheet, Amoc, Amazon are depicted along with their main interactions. The links between the tipping elements are color-coded, where red arrows depict destabilizing, blue arrows depict stabilizing interactions. Where the direction is unclear, in other words, is it stabilizing or destabilizing, the link is marked in gray. A more thorough description of each of the tipping elements is found in the text that follows. Where tipping cascade arises, the relative size of the dominoes illustrate how many ensemble members the respective climate components initiates tipping cascades in red domino, or how many tipping cascades the respective climate component occurs in blue dominoes. Standard deviations are given, and so on. So let me pull up the figure here. There we go. Okay, so disintegration of the Greenland ice sheet. Okay, destabilizing, so it weakens the Amoc, but Amoc could help stabilize the Greenland ice sheet. What do I mean by that? Okay, we know that the Gulf Stream brings warmth to the higher latitudes. Okay? If we destabilize the Amoc so that sinking slows, that means the Gulf Stream slows. That means the heat is not brought to higher latitude. Therefore, that could result in cooler conditions, which could slow the melting of the Greenland ice sheet. Right? We know what the adding of the fresh water does to Amoc. We know that destabilizes it. Well, not bringing the heat to high latitude could result in cooler conditions to slow down, reduce the melting of the Greenland ice sheet, and perhaps help stabilize it. Okay. Then they talk about, the link between Amoc and Southern Ocean heat accumulation. It's unclear as to perhaps destabilizing the West Antarctic ice sheet. So, for example, if you have increased ocean heat, you could bring that heat to the southern hemisphere, to Antarctica. But not to mention also that the southern oceans themselves are heating up. So we have increased heat content in the Southern Ocean, not only from whatever might be brought in from the conveyor belt, but just the regional waters as well that could disintegrate the ice sheet. But it's unclear what this contribution could be if Amoc slows down and the conveyor belt slows down. Hence, it's in gray. Okay? And the dashed lines indicate an unclear whether something will stabilize or destabilize. Disintegration of West Antarctic ice sheet, okay, could lead to sea level rise. Maybe we see sudden, as I just discussed, sudden ocean accumulation. Salinity gradient. If it increases, you get fast advection of freshwater anomaly. That's unclear of, because if you had freshwater, okay, yes, you get a stronger salinity gradient with a more pronounced halocline. I talked about that. I demonstrated that in my recent talks of what's going on in the Arctic Ocean. But what does this do to the freshwater? How does that treat the freshwater anomaly? For example, in the Arctic, does the freshwater stay or is it pumped out? So fast advection, that's movement of water. Okay? So that's unclear. So they're referring to, West Antarctic ice sheet melts, you get all this fresh water. What happens to that? What does that do to the salinity gradient? What does that do to stratification? What does that do to, along with the heat stratification? What does that do there? What does that do to a biological productivity? So we see the same thing here. I discussed in recent videos of a similar situation up here in the Arctic Ocean. And of course, these dominoes, the percent that the initiator of tipping cascade versus the occurrence in tipping cascades. Now, it's the recipient. So these are some of the interactions they're trying to get a handle on. It's like, if this happens, how does this affect that? How does this affect that? What's going on with the Amazon, the dieback of the Amazon? How does this all go together? And of course, they mention ENSO over here. Earth is a complex system. That's basically what they're trying to say here. Okay. Okay, so they say, based on a network from this expert elicitation and a Boolean approach founded on graph grammars, an earlier study found that the strong positive negative feedback loop between Greenland and Amok might act as a stabilizer to the Earth's system. Also, using the interaction network model of Kriegler et al. In 2009, it has been shown that large economic damages due to tipping cascade could arise with respect to the social cost of carbon. And then they go on to talk about other studies, quantify the economic impacts of single climate tipping events and tipping interactions. In the light of recent studies that hypothesize a considerable risk of current anthropogenic pressure triggering tipping cascades up to a potential global cascade towards the so-called hothouse state of the Earth system, I've discussed that with you in prior videos. We here aim at developing conceptual dynamic network model that can assess whether the interaction of tipping elements have an overall stabilizing or destabilizing effect on the global climate state. Okay. And they look at constraint from current observations and paleoclimatic evidence. Observations over the past decade show that several tipping elements are already impacted by progressing global warming. Ice loss from Greenland and West Antarctica has increased and accelerated over the past decade. Recent studies suggest that the Amundsen Basin in West Antarctica might in fact have already crossed a tipping point. The grounding lines of glaciers in this region are rapidly retreating, which could induce local marine ice sheet instabilities served by and influenced by the warming waters getting underneath the ice sheet, melting it from below. And it basically also suggests that parts of Antarctica, larger parts of Greenland might already have experienced strong ice retreat in the past, especially during the Pliocene. It has also been shown that Amok experienced a significant slowdown since the mid-20th century, which has led to the weakest Amok state in centuries. Models from Phase 5 of the Coupled Model into Comparison project, that's CMIP5, have shown that weakening of the Amok is currently largely caused by changing surface buoyancy fluxes, basically fresh water, right? Fresh water forcing the North Atlantic Ocean by meltwater influx from Greenland. An Amok slowdown also likely occurred during the last deglaciation, the Heinrich event, and the younger driest cold periods. The Amazon rainforest is not only directly impacted by anthropogenic climate change, including the increased risk of extensive drought events or heat waves, but also by deforestation and fire. In other words, the Amazon, with all those trees, been absorbing lots of carbon, called the lungs of the planet. Well, if you cut down the trees, you now have a carbon source, not necessarily a carbon sink. It is suspected that the Amazon rainforest could be close to a critical extent of deforestation, which might, along with global warming, suffice to initiate a critical transition. This could put 30 to 50% of rainforest ecosystems at risk of shifting the rainforest to a tropical savanna. or dry forest. Savanna, those plants draw down less CO2 than rainforest. Then you go to talk about the structure of the work. And so let me look at figure 2 here with you. Schematic overview of the generalized tipping element and time series of a tipping cascade. A, this one here, is exemplary bifurcation diagram of a tipping element with two stable regimes. The lower state indicates a stable baseline regime, and then the upper state indicates the stable transition regime. In other words, going from here, current conditions, to a new condition. For the Greenland ice sheet, for instance, there corresponds to a pre-industrial, almost completely ice-covered state, stable baseline regime, and almost ice-free state, stable transition regime, as can be expected in the long term for higher warming scenarios. There are two ways that a tipping element can transgress its critical threshold. It's called unstable manifold, and move into the transition state. Unstable manifold is this here. I'll enlarge this in a moment. An increase in the global mean surface temperature or via interaction with other climate components, I would say and or. In both cases, the tipping element converges to the stable transition regime indicated by the red hollow circles up there. B, that's this one here, exemplary line series showing a tipping cascade of two elements. Here, Greenland transgresses its critical temperature first. That is, it would become ice-free. Through its interaction with the West Antarctic ice sheet, the West Antarctic ice sheet then transgresses the unstable manifold in the vertical direction, following the path of the red arrow upward, directed arrow in panel A. This example is based on a scenario with global mean surface temperature increase of 1.6 C above pre-industrial levels in interaction strength D of 0.16. Okay, so let's enlarge this so we can get a handle what's going on here. So here's the stable baseline regime, and this is the state of the tipping element. So, tipping by global mean temperature increase. Right? So we increase the temperature, and see where it becomes a dashed line? This is the unstable manifold. Notice the transition from this current baseline to a new baseline. So we go from here, say a current temperature here, to a new temperature regime. It transitions eventually over to here due to perhaps coupling to other elements. Now, if you look at this one here on B, baseline regime, and we see what? This is in a, as I discussed in my prior video with the ocean tipping points, we have some dramatic change that happens, a drastic change that results in an abrupt change from one baseline to another baseline. That's what this diagram is showing. The light blue is the Greenland, the purple is the West Antarctica, green is the Amazon forest, and this blue is Amok. So basically what gets affected in an actual regime change is for the ice sheets, Greenland and West Antarctica. Rainforest and Amok, there are some changes, but it stays in essence within the baseline regime, according to this modeling. Okay. I'm not going to go through the methods here because they're just describing all the computer models and what they're doing on and so forth. I will, of course, leave the URL in the comments section. So if you're interested, you can then click on that and carefully read that and go through this if you so desire. So I will say this here. In the conceptual network model investigated in this study, the main dynamics of each of the tipping elements are condensed to a nonlinear differential equation with two stable states representing the current baseline state and a possible transition state capturing the qualitative dynamics of generalized tipping elements. And I refer to equation 1. Okay, nonlinear differential equations are Loads of fun to solve. Note the sarcastic tone. I've done my share of solving nonlinear differential equations. In fact, my own research involved sharing second-order nonlinear partial differential equations, which was a bear to do. Now, this is an interesting statement. In this study, we do not consider possible backtipping or hysteresis behavior of climate tipping elements as the forcing represented by global mean surface temperature anomalies only increase, never decrease. Right? Hysteresis, I did that one on Antarctica's ice, where that all the heat that's been put in, the temperatures increase, all that ice that melted as a result, even if you would removed the CO2 levels back to 250 parts per million, what have you, and cool the planet down to pre-industrial levels, not all of that liquid water would refreeze into ice. They talk about Amok here, and again, they referring to other research, some of the models used. But this is an interesting comment here. Paleoclimatic evidence suggests a bistability of the Amok in paleoclimatic records. Dansgaard-Oeschger events have been associated with large reorganizations of the Amok, where ice core data link the events to sea surface temperature increases in the North Atlantic. So in other words, when the sea surface temperature increases, okay, what you have is, and depending on what the salinity, what is the the freshwater content, the melting, and so on. But generally, if you increase in the temperature, you're going to put more fresh water on the surface, you're going to slow it down, and then vice versa. The critical temperature range for an irreversible disintegration of the Greenland ice sheet has been estimated between 0.8 and 3.2 C of warming above pre-industrial global mean surface temperature levels. Paleoclimatic evidence further suggests that there have been substantial, potentially self-sustained retreats of the Greenland ice sheet in the past. It has, for instance, been simulated that the Greenland ice sheet can disintegrate if warmer ocean conditions for the Pliocene are applied to initially glaciated Greenland. Greenland was nearly ice-free for extended interglacial periods during the Pleistocene. Sea level reconstructions further suggest that larger parts of Greenland could have been ice-free during marine isotope stage 11 in the Pliocene. Compared with the case of the Greenland ice sheet, different processes make the West Antarctic ice sheet susceptible to tipping dynamics. As large parts of West Antarctica are grounded in marine basins, changes in the ocean are key in driving the evolution of the ice sheet. The marine ice sheet instability can trigger self-sustained ice loss, where the ice sheet is resting below sea level on retrograde sloping bedrock. This destabilizing mechanism is possibly already underway in the Amundsen Sea region. Once triggered, a single local perturbation via increased subshelf melting could lead to widespread retreat of the ice sheet. Further, a recent study has shown strong hysteresis behavior for the whole Antarctic ice sheet, identifying two major thresholds that lead to destabilization of West Antarctica around 2°C of global warming, and large parts of East Antarctica between 6 and 9°C of global warming. And that's basically the basis for that video I did earlier. Conceptual models of the Amazon have identified multi-stability between rainforest, savanna, and treeless states, leading to hysteresis. This hysteresis has been found to be shaped by local scale tipping points of the Amazon rainforest, and its resilience might be dismissed under climate change until the end of the 21st century. More complex dynamic vegetation models also found alternative stable states of the Amazon ecosystem and suggest rainforest dieback might be possible due to drying of the Amazon basin under future climate change scenarios. In other words, you lose the rainforest. While it remains an open question whether the Amazon is a single system-wide tipping point, projected increase in droughts and fires is likely to impact the forest cover on a local or regional scale, which might spread to other areas. In contrast to the ice sheets and ocean circulation, the rainforest is able to adapt to changing climatic conditions to a certain extent. Don't forget, you got that specific heat of water to contend with. However, this adaptive capacity might still be outpaced if climate change progresses too rapidly. So this is a kind of another, they're citing a lot of papers here. This is kind of another literature review. So they describe, physical interpretation. Increasing freshwater input from enhanced melting of Greenland ice sheet can lead to a weakening of Amok. We already know that. We're seeing that now. Supported by climate evidence as well as modeling studies, and just look at what's happening now. Paleoclimatic records further suggest that Amok could exist in multiple stable states based on observed temperature changes associated with meltwater influx into the North Atlantic. Therefore, it is likely that a tipping of the Greenland ice sheet would lead to a destabilization of Amok. Conversely, if Amok weakens, leading to a decline in its northward surface heat transport, Greenland might experience cooler temperatures, which would have a stabilizing effect on the ice sheet. With version 3 of the Hadley Center Global Environmental Model, that's the above 5C scenario, it has been shown that temperatures in Europe could drop by several degrees if the Amok collapses, regionally up to 8 degrees C. A cooling trend in sea surface temperatures over the subpolar gyre as a result of the weakening Amok has been confirmed by recent reanalysis and observation data. This fingerprint, quote unquote, translates a reduction in overturning strength of 1.7 centigrades per century to 0.44 Kelvin sea surface temperature cooling per century. Now, Kelvin has the same gradation as Celsius, but they're using Kelvin. Okay, they use Kelvin. Okay. Amok regime shifts between weaker and stronger overturning strength during the last glacial period have been associated with large regional temperature changes in Greenland. And again, they cite the Dansgaard, Ershger, or Heinrich events. Moreover, there is paleoclimatic evidence from 3.6 million years ago that a weaker North Atlantic current as part of the Amok fostered Arctic sea ice growth, which might have preceded continental glaciation in the Northern Hemisphere at that time. Based on these findings, we assume that a weakening of Amok would have a stabilizing effect on Greenland ice sheet. Now, when I first started my channel 3 years ago, I made the argument that slowing or shutting down of Amok will lead to cooling conditions and possibly tip over into an ice age. That's basically what they're saying here. However, because of the high ocean heat content, I no longer hold to that assessment. There's so much, yes, Amok might slow down and shut down, but you still have all this heat in the ocean that will diffuse into the atmosphere. And you put that warmth into the atmosphere, you're going to continue to melt. So I no longer subscribe to that assessment that just because Amok slows or shuts down, that you're going to reverse the warming trend and bring on cooling conditions. There's just so much thermal inertia in the system that I see just from the fusion of heat energy into the atmosphere alone, because it can't be sequestered to death, will continue the warming trend. So I'm going to disagree with them a little bit there on that point.
There may very well be regional cooling, but I definitely do not see at least hemispheric or global cooling because of all that heat energy in the oceans.
West Antarctic ice sheet to Amok. It remains unclear whether increased ice loss from West Antarctic ice sheet has a stabilizing and destabilizing effect on Amok. Swingadow Swingadow et al. Identified different processes based on freshwater hosing experiments into the Southern Ocean, which could be associated with a melting West Antarctic ice sheet. The authors found both enhancing and weakening effects of Amoc strength. First, deep water adjustments are observed. This means that an increase in the North Atlantic deep water formation is observed in response to a decrease in Antarctic bottom water production due to release of fresh water. Basically, fresh water reduces the density. That bottom water doesn't form. It doesn't dive down. It's not so dense. Well, you have volume constraints. You have conservation of volume. If you don't have that Antarctic bottom water going north, well, that allows for more North Atlantic deep water to fill in the missing space. Is basically what they're saying. Second, salinity anomalies in the Southern Ocean are distributed to the North Atlantic, which dampens the North Atlantic deep water formation. Third, the North Atlantic deep water formation is enhanced by a strengthening of southern hemispheric winds in response to southern hemisphere cooling. The reason for the stronger winds is the greater meridional temperature gradient between a cooler Antarctic region and the equator. And this has been called the Drake Passage effect. Overall, the first and third mechanism tend to strengthen Amoc, whereas the second would rather lead to a weakening of Amoc. Timescales are not yet clear. And what about Amoc affecting the West Antarctic ice sheet? What interaction from Amoc to the West Antarctic ice sheet is destabilizing. If Amoc shuts down, sea surface temperature anomalies could appear. As the northward heat transport is diminished significantly, this could lead to a warmer south, colder north, and then a warmer south would lead to more heat melting the West Antarctic ice sheet. And then Greenland all the way to West Antarctic ice sheet. What about those interactions? The direct interaction between Greenland and West Antarctic ice sheets via sea level changes can be regarded as mutually destabilizing, although with different magnitudes. It's well known from tidal changes that grounding lines of ice sheets are varying. Therefore, the Greenland ice sheet and West Antarctic ice sheet could influence each other by sea level rise if one or the other cryospheric elements would melt. Okay, that's the essence of that one. What about Amoc affecting the Amazon rainforest? The interaction between Amoc and Amazon rainforest is set as unclear. It is suspected that the intertropical convergence zone would be shifted southward if Amoc collapsed. The intertropical convergence zone is actually off in the Pacific Ocean. This could cause large changes in seasonal precipitation on a local scale and could have a strong impact on the Amazon rainforest. Okay, but basically it's unknown what those effects are. So now they go into a lengthy discussion, a lot of math here, and what they're doing with the modeling and so on. I'm going to skip over the rest of this here. Figure 3, time series of tipping cascades. Exemplary time series of states for each of the 4 investigated tipping elements. Let's see if this will enlarge. Not really. But basically we got Greenland, West Antarctic, Amoc, Amazon rainforest. And as you can see here, we can see some abrupt changes going from one state to another state. This looks like I'm trying to read the scales here. So we have interaction strength increases going down. So see the strength going from 0.08 to 1.6 to 2.4. And then the change in the global mean temperature, 1.4, 1.5, 1.6, 1.7. So in other words, 1.4 warmer, 1.5, 1.6, 1.7 warmer compared to pre-industrial temperatures. So that's what's going on here. And then we see the changes in state. As you can imagine, as you increase the strength, along with an increase in the temperature, we get the most dramatic changes in that scenario. The highest increased strength, highest increased temperature. So they set the parameter settings the same. They did the temperature changes across the top. And let's see. Tipping cascades shown here are defined as the number of transitioned elements at a fixed interaction strength along with the change in temperature. If between these two simulators some of the tipping elements after the equilibrium state, a tipping cascade of respective size occurred and is counted as such. A single tipping event for an interaction strength of 0.8, and A, that's what A is. Tipping occurs at 1.6 degrees C. Okay, so let's go back up and look at that. So what they're saying here is that with a strength of 0.08, we don't see tipping until we get to about 1.6. Right here, it moves from one state to another. So for 1.4 C, warmer, we don't see any tippings no matter what the strength is. The same is true for 1.5. It's not until you get to 1.6, 1.7 that we see a change, a transition, a tipping threshold initiated. And the stronger the strength of the interactions, right? This is interaction strength. The stronger the interactions, then the more dramatic will be the transitioning. That's kind of the take-home message from this graphic here. So when we look at the strength here, to talk about how much the things interact, Greenland to the other Greenland, West Antarctica, Amok, Amazon, okay, all taken together, how much they interact with each other. When we get to temperature of 1.6, we start seeing transitioning. And you know what, folks? We're approaching that now. In fact, we might already be past 1.5. So it's already happening. They continue to describe basically what I just summed up for you. Again, I'm going to leave you the URL. We mark the baseline transition regime as gray hatched areas. Between the hatched areas, the state is not stable and a critical state transition occurs. Lower gray area, the element said to be in the baseline regime. Upper gray region, it's in the transition regime, right? So unstable in the white, that's the baseline, that's the transition. So I want to get right to results here. The shift in effective critical threshold temperatures due to interactions. Owing to the interactions between the tipping elements, their respective critical temperatures are effectively shifted to lower values except for Greenland, for West Antarctica and Amok. We find a sharp decline for interaction strength up to 0.2 and an approximately constant critical temperature range afterwards. Effective critical temperature for the Amazon is only marginally reduced due to the interactions with the network.
I'm going to end the video here. This will be the conclusion of part 1. In part 2, I will pick up continuing with the results and the further discussion that the paper provides. So stay tuned for part 2. That will be the next video in this 2-part video series. Thank you for your time.
Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.